In this video, we'll do a curve sketching example, and we're going to try to sketch the graph of the function f of x equals x over 4 minus x squared. So the example gives us that function, and it also just gives us the derivative and the second derivative. So I'm giving you those just to save a little bit of time. And I want to sketch the curve of f in the following steps. All right, so I'm going to follow the general structure that our book adopts in terms of showing the work that leads up to the graph of f. And I'm going to label my steps with the letters. So the first step, A, is to find the domain. Find the domain of the function. So recall that to find the domain, I got to think about my restrictions. The restrictions that we have on the inputs. And with this function, there's only one type of restriction, because I have a fraction. It's that the denominator, 4 minus x squared, is not allowed to be equal to 0. So if I think about when this happens, when is 4 minus x squared going to be equal to 0? That only happens if x is 2 or negative 2. So we better have that x should not be allowed to be equal to 2 or negative 2, because those values would have made the denominator be 0. Okay, so the domain is going to be everything except for 2 and negative 2. All right, so that is the first step. Step B is to find the intercepts. So maybe up here I should say domain. Domain is all reals except plus or minus 2. All right, let's talk about finding the intercepts. So for the intercepts, let's do y-intercept first. That's usually easier. We find this by setting the x equal to 0. And if you set x equal to 0, I'm going to just skip that step. But if I plug it in, I'll get 0. Okay, so the y value will be 0, and we end up getting the point 0, 0. For the x-intercept, we set the y value equal to 0. And if you set the y value equal to 0, and you solve that resulting equation, you'll get x equals 0 as well, it turns out. So the x-intercept is also 0, 0. So I skipped some steps here. I skipped this work. Okay, all right, let's move on to the next step. So when you do problems like this, I definitely want you to demonstrate that work to me. It's just quick, which is why I'm skipping it for the purposes of the video. All right, so next step, C, is to find symmetry. So test to see if this is an even or an odd function, or neither. So I want to give you an opportunity to try that. So pause the video for just 1 minute and test this to see if it's even or odd. 4, 3, 2, 1. Pause it for a minute and test it for its symmetry. Alrighty, so hopefully you did that. Hopefully you paused it for a minute to try this. Let's talk about it now. So remember, I plug in negative x. And when I do that, I'll get negative x on top, and on the bottom I'll get 4 minus negative x being squared. So this is, the bottom just becomes 4 minus x squared, because when I square that negative will go away. And then the negative on top, let me move it in front of the fraction, and I'll have the x on top. So this is just negative of the original function, f of x. So that makes this an odd function. So when we go to graph it, we're going to make sure that the graph is symmetric about the origin. So knowing the symmetry is helpful, because if I can figure out what the graph looks like on one side of the y-axis, on one side of the origin, then I'm automatically going to know that it's got to be the mirror image of it on the other side. So we'll see how we use that symmetry about the origin later when we go to graph this. All right, we're on to step D, which is to find asymptotes and holes. So find asymptotes and holes. Okay, so we reviewed this. We reviewed these in this section as well. So I want to give you another chance to try this. Pause the video for, let's say, 2 minutes to find the asymptotes and holes. 4, 3, 2, 1. 2-minute pause to try this. Alrighty, so hopefully you did that. Hopefully you paused it and tried it. Let's talk about it. So remember, our function was x over 4 minus x squared, which I can factor as x over, the bottom is a difference of squares. It'll factor as 2 minus x times 2 plus x. Alrighty, so my vertical asymptotes, because this is a rational function, it's just a polynomial over a polynomial, my vertical asymptotes come from factors in the denominator that don't cancel completely away. And in this example, nothing canceled away. So I'm going to get a vertical asymptote from what makes 2 minus x be equal to 0, and that's x equals 2. We'll also get a vertical asymptote from what makes 2 plus x be equal to 0, and that's x equals negative 2. And if there was a factor on the bottom that canceled completely away, that would give me a hole. But in this case, none of the factors on the bottom canceled away, so there are no holes. There are going to be no holes in this graph. All right, and we are now ready for the horizontal asymptotes. So let's do the limit as x approaches infinity of this function, and also as x goes to negative infinity. So if x over 4 minus x squared, because this is a rational function, I'm going to use my shortcut for these infinite limits. And that shortcut says, just keep the highest power term on the top and the highest power term on the bottom. So on the top, that's x. On the bottom, that's negative x squared. So I can simplify this to the limit as x goes to infinity of negative 1 over x. And this is going to be negative 1 over infinity, and that's going to 0. Okay, similarly, we could show that the limit as x goes to negative infinity of our function also will be equal to 0. So our horizontal asymptote, there's just one of them, in both directions, in the infinity direction and in the negative infinity direction. Our function is getting that y values are getting really close to 0. So the horizontal asymptote is y equals 0. All right, so we are ready for the next step. So step E is to find the intervals of increase and decrease. And along with that, we can get the local extrema. So we can test to see whether we have local maxes or local mins, or neither at our critical numbers. In the textbook, it splits up this step into 2. It does intervals of increase and decrease as step E, and then testing our critical numbers for local extrema as step F. I'm going to just combine that all into one because it's all going to be related to the same number line. Okay, so I had already said what our derivative is. Recall our derivative, after it's simplified, is x squared plus 4 over, what is it? On the bottom, it's 4 minus x squared being squared. So I'm going to need to figure out when this equals 0 and when it's undefined. So this whole function, for it to be equal to 0, the numerator would have to be 0, and the numerator actually never equals 0. So this whole fraction never equals 0, since for the numerator to be 0, we'd have to have x squared be equal to negative 4. But we're only allowing real numbers in our class, so x squared can never be equal to a negative number. This is never going to be equal to negative 4. Okay, I also got to find when this whole derivative is undefined. And it's going to be undefined when the bottom is 0. And that happens when x is plus or minus 2. All right, so we take these values, we plot them on a number line. Okay, there was nothing that made the whole thing be 0, but there were 2 values that made it undefined, so I will put those on the number line, negative 2 and positive 2. And then I start to make my sign chart. So I'll put all the factors of my derivative as rows. So I'll have x squared plus 4, and then I'll put the whole denominator, 4 minus x squared, that quantity squared, and then I can combine them to get the sign of my derivative and write down what that tells me about the original function, f of x. Okay, so I make some rows, and I make some columns at these values, the negative 2 and the positive 2. So with the x squared plus 4, it turns out this is always positive. So I might be able to see this sort of logically. If I couldn't think about it logically, I could pick a test point in every single region and plug it in, and I could notice it's always going to be positive. Or I could visualize the graph, and the graph of x squared plus 4. So it's like the x squared parabola. but the plus 4 shifts it up 4 units. So the vertex of it is 4 units up. But notice that the y values of this are always positive. And that's how we can also tell that this is always going to be a positive output. With the next factor, because of this even power, this squared, on this whole thing, that's going to guarantee this is never negative. This is always going to be positive as well. Okay, and then dividing two positives gives me a positive. So my derivative is going to be positive in all of these. And when my derivative is positive, the original function is going up. It is increasing. Here as well, going up, increasing. Here as well, it is increasing. So my function, my original function f, put a bullet point here, is increasing on the interval from negative infinity to negative 2 union. Negative 2 to positive 2 union. 2 to infinity. Even though these are consecutive intervals, they're sort of back to back, and the same thing is happening, it's just increasing on all of them, I can't just combine these into one. And that's because the original function was not continuous at negative 2, and it was not continuous at positive 2. And we actually kind of saw that here as well. There's vertical asymptotes at 2 and at negative 2. So because of that, I won't be able to say, oh, it's just going to be increasing the whole way. The vertical asymptotes kind of split up what's happening. Alrighty. So it's decreasing on those intervals. F is never decreasing. Never decreasing. And then the other part of this step was for local extrema, but there's nowhere that my function changes from increasing to decreasing or decreasing to increasing. So there's no local extrema. No local extrema either. All right, so we are ready for the next step. So that, I think, was step E. We were ready for step F. So we did increasing, decreasing. We now want to find the intervals of concavity. Intervals of concavity, and what comes with it are inflection points. So I'll say concavity plus the inflection points. All right, so remember, our second derivative was 2x times x squared plus 12 all over 4 minus x squared being cubed. So I just told you what it was after it's already simplified and factored. I want to give you an opportunity to try this first. Okay, so I want you to pause the video for about 3 minutes. See if you can identify where it's concave up and down and where the inflection points are based off of this second derivative. 4, 3, 2, 1. Pause it for 3 minutes to try this. Alrighty, so hopefully you did that. Hopefully you paused it and tried it for 3 minutes. Let's talk about it now. So I first need to figure out when is this equal to 0 and when is undefined. So this is going to be 0. For this fraction to be 0, I need the numerator to be 0. And that will happen from this first factor when x equals 0. But from the x squared plus 12 factor, well, that's never going to be 0 because that would mean x squared has to be negative 12. And x squared is not going to be a negative number. It's never going to be negative. It's always going to be non-negative. All right, so this is only equal to 0 when x is 0. When is it undefined? It's undefined when the bottom is 0, and that happens when x is plus or minus 2, just like before. So okay, so I make my number line and I plot these values on it. So I'll have negative 2, I'll have 0 as well now, and I'll have positive 2. And then I'm going to make a row for the factors that I see. So I'll do 2x, x squared plus 12, and then 4 minus x squared. Let's just put that whole thing being cubed. And then I can form my second derivative, and then I'll write down what that tells me about f of x. Okay, I'll separate out rows. And now let's separate out columns. Okay, and for 2x, that's going to be positive to the right of 0 and negative to the left-hand side of 0. With x squared plus 12, it's really similar to the x squared plus 4 factor, except the parabola is going to be shifted up even more. So the outputs are definitely all going to be positive. This is all going to be positive. I could also just think about it algebraically. X squared is always greater than or equal to 0. So when you add 12 to it, that whole thing is always going to be greater than or equal to 12. So definitely always positive. Okay, with 4 minus x squared cubed, Because the cube, this can sometimes be positive and sometimes be negative. So I need to know when is 4 minus x squared positive and when is it negative. And this is where referring to the graph can help me. Y equals 4 minus x squared. With these quadratics especially, it can be helpful to graph them. So the minus x squared means it's going to be an upside down parabola. And the 4 will shift it up 4 units. So it'll be like this, where that vertex is 4 units up. The x-intercepts of this, the things that make the y value be 0, are 2 and negative 2. So 4 minus x squared is going to have a positive output, a positive y value, when I'm between negative 2 and positive 2. And then when I cube it, when I cube the positive number, it'll stay positive. So it'll be positive in between negative 2 and positive 2, but outside, to the right of 2 and to the left of negative 2, this is negative y values. And when you cube negative y values, they'll stay negative. Okay, and now when we combine, let's see, 2 negatives and a positive make a positive. 1 negative and 2 positives will make a negative. 3 positives will make a positive, and then 2 positives and a negative will make a negative. Okay, so when the second derivative is positive, f is concave up. Here as well, it's concave up. And when it's negative, f is concave down. Concave down. So writing that down, our function is concave up on the intervals from negative infinity to negative 2 union the interval from 0 to 2, and it's concave down on the other intervals, negative 2 to 0, union 2 to infinity. And the inflection points. So remember, for something to be an inflection point, it's got to be a place where the concavity changes, but also my function needs to be continuous there. And if we look to our number line, well, the concavity changes at all of these, at negative 2, at 0, and at positive 2. But if I think back to my original function, so here's my original function. Remember, 2 and negative 2 were not even in this domain because they made the denominator 0. So my function is definitely not continuous at 2 and negative 2. So they can't be inflection points. So there's only going to be an inflection point at x equals 0. And I'll write that reason down again. So f is not, it's not continuous at x equals plus or minus 2. So these can't be inflection points. That's very important. This is a common error that folks make with these problems, just thinking, oh, anywhere the concavity changes, that's an inflection point. But we got to be careful. It's also got to be a place where the original function is continuous. Okay, this question said, tell me the whole point. It didn't just say the x value. So if you were to plug in x equals 0 into the original function, it turns out that y is also 0. So the point is 0, 0. That's where the inflection point will be. And now that we have this, we are ready for step G, the last step, which is to finally sketch the graph. To sketch the graph. And the key to this is to begin by combining the sign charts of the derivative and the second derivative. And this we've seen before. So I'm going to make my number line. So any number at which I put a tick mark in either the f prime sign chart or the f double prime sign chart goes on this one also. So on the f prime sign chart, we had tick marks at negative 2 and positive 2. In the f double prime sign chart, we had tick marks at negative 2, so that we already got. Positive 2, we already got. And also a 0, so that one I need to put in. All right, and now I'm going to keep track of my derivative, my second derivative, and what that tells me about the shape of f. So I'll separate out some rows and some columns. So if I go back to my sign chart for the derivative, so the sign chart for the derivative, for the first derivative, let's see, this is the one that was positive everywhere. Okay, so I will draw this being positive everywhere. Positive everywhere. And for the second derivative, let's see, this one I think alternated. So it started off positive and then went positive, negative, positive, negative. And I can just do that same thing here because the tick marks in this number line ended up being exactly the same. Okay, so I get positive, positive here, and then the other two are negative to alternate. All right, so we're ready for the shape of f. I'm going to do the first column slowly, and the rest I'll do more quickly. So if the derivative's positive, my function is increasing. The second derivative's positive means it's concave up. So that means it's going to have this sort of shape, increasing concave up. The next column is increasing concave down. The last column as well, increasing concave down. And the third column is the same as the first, increasing concave up. All right, so now we are ready. We are ready for the graph. We are ready for this graph. So remember, our function was f of x equals x over 4 minus x squared. Let me zoom it out a little bit so I can still see the number line. All right, so I'll draw some axes. And we'll put some tick marks. Well, I'll put tick marks at relevant points. So I'm going to begin by plotting the points that I know for sure where they are. So we found intercepts. The only intercept in this problem was 0, 0. That was the x-intercept and the y-intercept. So I'm going to label that 0, 0. I'm also going to draw the asymptotes. Usually I want to draw the asymptotes and intercepts first. There were vertical asymptotes at 2 and at -2. So I'll draw in those first. So let's draw in those vertical asymptotes. And there was a horizontal asymptote at 0. That means it's right on the x-axis. So right on the x-axis there will be a horizontal asymptote. Okay. And now let's start to draw in the shapes of the graph. So to the left of -2, my graph needs to have this shape. So I want to think about also, as x goes to -infinity, was my graph going to approach this horizontal asymptote? That's where I can look back to my limit. So we said earlier that similarly, as we took the limit as x goes to -infinity of our function, that's going to be equal to 0. So if I go to the graph, my function does need to approach, it needs to have this shape and then approach this horizontal asymptote as x goes to -infinity. So that's going to be this sort of shape. Another way I can sort of tell that it's going to lie above like that and not do something like this, besides the fact that this wouldn't approach that horizontal asymptote, is now this graph has another x-intercept. But earlier when we solved for x-intercepts, the only one there was supposed to be was at the origin, at 0, 0. So that rules out this from happening. All right, and now between -2 and 0, our graph is going to have this shape, increasing concave down. That's going to look something like this, and it's going to snuggle up next to this vertical asymptote. And then in between 0 and 2, it's going to go to increasing concave up. It's going to snuggle up next to this vertical asymptote. And then similarly to what we did on the left-hand side of -2, on the right-hand side of +2, our function has this increasing concave down shape. And it's going to go like that. It's going to snuggle up next to that horizontal asymptote. And I know it's going to get close to the horizontal asymptote from this side also because we took the limit as x goes to infinity. So this is going to infinity, positive infinity, and that one was also 0. Okay, so that what indicates to me that it also gets close to that horizontal asymptote on this end. And that is my graph. So finally, returning to our goals for this section, we finished the last goal. We did an example where we sketched the graph of a function using the derivative, the second derivative, and all that other information about symmetry, domain, holes, and asymptotes.